I'm Robert. This is work done with all these people at the University of Copenhagen, as well as Magnus from Aarhus. And I believe they're all in the room right now. I don't know about that. The context of this is that this is done in Futhark, which is a functional array language. It's designed to study the compilation of array languages, and there's a few important things that you need to know about it for this talk. First of all is that space is function application. Functions are curried, which means that every function really only has one argument. So f of x, y, z means this thing with the parentheses. And it has a Hindley-Milner style stack type system, which means it has parametric polymorphism. And as an example of a Futhark program, this computes the dot product. You can see that all the function applications is just when done with the space. And yeah. So what is rank polymorphism? So if you have just normal scalar addition here, 1 plus 2 equals 3, the idea is that we can lift that addition operator to work on higher dimensional inputs. So here we have two vectors, 1, 2, 3, 4, 5, 6, and it adds them piecewise. And it will also, here you can also add a vector and a scalar, and it will replicate the scalar appropriately to add it to the vector. And it's not just for infix operators, it also works for functions. So here we have square root applied to this matrix, and it does it piecewise in the obvious way. So to summarize what that all means, it's roughly, rank polymorphism is roughly the ability to apply functions to arguments with different ranks than the function actually expects. And the benefit, at least in our context here, is that it makes code easier to read, and it more closely matches the math that you're trying to describe with the code. So for example, map plus is not as readable as just putting the plus in its proper infix location without the sort of administrative map that we have there. And also in practice, basically every popular rank polymorphic language is dynamic, so it's very uncommon to have this feature with a static type system, especially with parametric polymorphism, because those things all make it hard to do. So some background about some functions that we'll use in this talk. There's map. I'm sure everybody here knows about map, but mapping, you take a function and you apply it to every element of some input array in the obvious way. And our map here can also take many arguments for for functions that take more arguments. So plus takes 2. So you give it 2 arrays and it does the obvious thing. So the first element here is the first element of each array added together, and so on. And then rep corresponds to replicate. But the unique thing here is that we don't actually describe how long the replicate array should be. For this talk, we just sort of ignore that issue. In actuality, Futhark can actually do some size inference and figure out how long this thing should actually be. But we're not going to talk about that. So just don't worry about how long the array should be. So for an example of how we can do rank polymorphism with map and rep, if we are trying to add this matrix here to the scalar, what we first do is we have to lift the scalar to also be a matrix. So every rep adds a dimension, so we rep twice. And now we have some 2-dimensional thing on the right. We don't know exactly the length, although it will, in this case, it will match the matrix. And then we have to also lift the addition operator here with maps. And then this whole thing will then to every entry here, we'll add a 1 using this elaboration. Of course, it's not just for infix operators. It works for any kind of function. So here we have some input XSS, which is a matrix, and we have some function, which has that type. It takes a vector and a matrix and gives you an integer. And now we want to make f of XS rank correct. So what we first do is we first map the first application, because it's being applied to a matrix, but it expects a vector, so we can map with the function. And then we have to also rep the second argument, because this map has, in a sense, inflated the dimensionality of the function. And so we have to overcome that with this extra rep, essentially. And you can see that with the type of map of fxs here. And you might think, well, you don't really want this rep. And in practice, you don't actually need it, because many reps like this that you need because of previous maps can be fused away. So you can often get rid of these maps, these extra reps by fusing them into the function by doing this lambda expansion right there, eta expansion. So our goal to make rank polymorphism work in Futhark is to essentially insert these maps and reps automatically, and to make the function application rank correct. And there are a few challenges involved with this. The first one is that there's ambiguity, so there's often many ways to do this elaboration that are in a rank correct way. So here's an example where we have sum and length, and we're applying these things to a matrix. One possible rank correct elaboration here is we first take the length of the matrix, which of course gives you a scalar, but sum expects an array or a vector, and so this is no longer rank correct, so we have to insert this rep here to make this thing work. Many of you probably think this is kind of a gross elaboration, and the actual one that you would probably want is this one, where you map the length over the matrix and then you sum up those. But of course, there's in fact infinitely many ways to do this, because you can always insert extra reps to overcome maps and keep doing this forever and ever and ever. So in this case, there are actually infinitely many ways to actually make this thing rank correct. So the question is, how do we choose? And to choose, we've invented two rules here. And the first one is that we say that an application can be mapped or repped, but it can never be both. And so just as examples of things that are okay. So in this first example, obviously you just have a map, so it's okay. In the second example, you have two reps, that's okay. You can have any number of reps, you just can't have both map and rep. And in the third example, you might think that's not okay, but the point is that the h actually takes two arguments here. So in the first argument, then the first application is just to h to x, so we've just mapped it twice there. And then in the second application, which is to y, there we've repped it. So that's also still okay. But what isn't okay is mapping and repping in the same application. So here f is just applied to x, so it's considered the same application, and that's illegal. And also in the second example there as well. And the point is that it's never necessary to map and rep in the same application, because you can always get a rank correct program without doing this. So it's an easy way to disambiguate possible, or to eliminate possible elaborations. As the second rule, our goal is to minimize the number of inserted maps and reps. And we found that, in general, this aligns with what the programmer actually intends to do. And it's a simple mental model. It aligns with what the programmer actually intends, generally, because you don't intend to insert superfluous maps and reps yourself. You tend to do the minimal possible thing to make the thing work. The minimization happens over every single application in a top-level definition. So it's sort of a global minimization over each definition. And the reason why Rule 2 also helps us with ambiguity is because you want to choose from the minimal possible elaborations. So if we go back to the sum of length of XSS, there's only two possible minimal ones. And they're minimal because each one inserts a single rep or a single map. And so we've whittled it down, to just these two choices. Of course, you still have these two choices. So in this case, Futhark would actually say, send an error and be like, wait, I have these two possible choices, you have to choose. And a challenge, again, is that this minimization process is global. And it also, every application requires you to consider, so in sum, for example, here, when we're considering how to elaborate length of XSS here, we only know to map it because there's an outer sum. So to know how to map the inner application, we have to also consider the outer application. So you can't do things locally. You have to consider all the applications at once. And that's also another challenge. Okay. So yeah, you have to consider all applications simultaneously. And another challenge here is that, of course, Futhark has parametric polymorphism, which means that functions can have type variables. And the problem with type variables is that they can have any rank, so you don't know anything about them. And so the question is, how can you statically insert these maps and reps in the presence of these type variables whose ranks you do not know? And to begin answering these questions and how we solve these challenges, let's look at constraints. This is a constraint-based system. If we're just looking at a function application, so here we have some function, it takes some parameter type P, it has some output B, and it takes some input with type A. And we're looking at f applied to x here. In a normal application, we just have the constraint P has to equal A, right? To apply the function, the parameter type has to equal the argument type. We only care about rank, of course, so we relax this requirement to say that the rank of P has to equal the rank of A. And this double bar notation just means the rank, or the number of dimensions that the thing has. So just as an example, this is the type of matrix, so dimension, integer. So it's a matrix of integers, and of course that has rank 2. And just integers is a scalar, it has rank 0. So, of course, rank polymorphism means the rank indifferences are allowed. So how do we encode this? And what we do is relax our constraint further. And there's 2 cases. In the first case, this is when the parameter type has a rank that's lower than the argument type, and this corresponds to a map. So what we do is we introduce a rank variable here called m for map, and that accounts for this difference between the rank and the parameter and the rank and the argument. So if we're looking at a square root applied to this vector here, we get this constraint here. So this integer here corresponds to what the square root expects. It expects a scalar, and that has rank 0. But we've applied it to a vector, which has rank 1. And then we have this equation, and from that equation, we can solve that m equals 1, and that means that we need a map to make this thing rank correct. So from this constraint, we've deduced that that a rank correct elaboration here is put a map in front of the square root. Similarly, in the other case, when your parameter type has higher rank than the argument, we introduce another rank variable, r for rep, and we play the same game. Here we're using length. I know length itself is a little bit of a funky thing in terms of repping, but ignore that. So just look at the constraint just to understand. So if we're applying length to 3, we're going to have to rep that 3. And an important thing here is that now, because length itself has a type variable, we get a type variable in the actual constraint. And of course, you don't know what the rank of this thing is. You just know that it's some type variable. So that just persists in the equation. And what happens is that then r can be any value. There's infinite many solutions here because of the rank variable, because that rank variable can assume many different ranks. So what happens is that this constraint means that we have infinitely many different possible elaborations here. Thanks. So if we take all that together, of course, when we apply a function to an argument, we don't know if we should map or rep statically, right? So we have to include for the possibility of both. So we include both an m and an r in our rank equation. But of course, rule 1 says that we can't map and rep. I mean, together we can only do one or the other. So that means we have to add additional constraint here, which says that either the m is 0 or the r is 0. And then the way that this proceeds is that we go through a top-level definition, and we generate these constraints. So this one, these 2 right here, for every single function application. Just to show you how this works, if we're looking at sum, so this is 2 different functions, right? Sum of length of some matrix. We first generate the constraints here for length, just as we did before. And then we also generate the constraints for sum. And notice here also that sum, the m1 from length also appears here in sum. And that shows that how you choose m1 will affect how you choose the rank variables for sum. So the whole thing, different applications affect different applications in this elaboration. And of course, rule 2 says to minimize the number of maps and reps, right? So let's also encode that. And exactly the number of maps and reps is exactly these variables, right? And now it's starting to look a lot like an ILP. There's just one problem, which is that these OR constraints are not linear. But you can play some ILP magic. I won't go into it here, and you can linearize them. And so that's what we do. And so we get this ILP. And so the TLDR of how this whole thing works then is that for every application, we generate a rank equality and rule 1 constraint, which is the OR constraint. We can transform the constraint set into an ILP and solve, so exactly this thing. And then we use our ILP solution to elaborate the program with the implicit maps and reps. So here, for example, if your ith application in this program, which is f of x, and we saw the ILP says that m sub I should be 3 and r sub I should be 0, then of course you insert 3 maps and you don't insert a rep. And then you have an elaborated program that is rank correct, not necessarily type correct. And you just take this thing and you continue with compilation, and the rest of the compilation pipeline has no idea about rank polymorphism whatsoever. So how does this look for the user? Map and rep are nothing special. They're normal fruit-like functions. The programmer is free to write both of them in their source code. And what this means is that the programmer can use AUTOMAP to whatever extent that they wish. So if they don't want to use that at all, they just use explicit maps and reps wherever, and there's no inference at all. If they want to use it somewhat, they can make some things implicit and some things explicit. Or if they want to use it maximally, they make everything implicit up to ambiguity. And on the note of ambiguity, so we saw this example before with sum of length. In this case, we cannot decide which one to choose, right? So what we do is we trigger an error, but our error can be exactly this message. It can say sum of length of blah, blah, blah can be elaborated into these two possibilities. We can give it as explicit feedback statically to the user. And then disambiguation is very easy because these things are just normal fruit-like functions. The programmer can just insert a map or rep themselves into the program. And of course, it's fully transparent because the compiler can always elaborate any implicit program into an explicit one. So you as a programmer can always say, hey, what does this program actually look like explicitly, and the compiler can tell you exactly what it's doing. So the practical impact of this, it's hard to exactly quantify because it's just syntactic sugar, right? What we did, though, is we took our benchmark suite and we rewrote the programs in it to take advantage of AUTOMAP when we thought it would increase clarity. And here's just an example of a program. So this thing is sort of cluttered with all these administrative maps. And it sort of obscures what's actually going on here. But with AUTOMAP, we can get rid of all of them. We do have to include some reps here, but that's OK. And you can see, like, for example, these QRs and QIs at the bottom are much simpler and are much closer aligned with the math that they're actually trying to express. Some metrics from our benchmarking. So the key takeaway here is that most ILPs that we generate are very small. Some of them, like this 28,000 thing, is kind of big, but that's largely a product of the fact that the implementation is very unoptimized, and we can remove many constraints that are being generated. And even with our very unoptimized implementation, type checking slowdown is about 2.5 times. So it's in practice very usable. For related work, I'm only going to talk about typed systems. There's typed remora, which is a very general and powerful system. And unlike us, they actually express rank polymorphism at the type level themselves. So they bind shape variables here. For example, this could be the type signature of a sum, that can collapse an array of any dimension into a single scalar, which we cannot express in our system. But unfortunately, inference is very difficult and still is an unsolved problem. There's also the Napoleon functor work by Jeremy Gibbons. And this is a rank polymorphism encoding in Haskell, which is also very cool. But it leads to some complicated function types for the user. It also requires a very sophisticated type system with dependent types or dependent like types. And the error messages are potentially not so great. And then, of course, there's single assignment C. This is probably the most popular or version of rank polymorphism in a typed system. It doesn't have parametric polymorphism or higher order functions unlike us, but it has some cool stuff, especially here, rank specialization, where you can specialize what a function does based off of the rank of the input. And you can do some cool stuff with scans, and you have a paper about that. So in summary, AUTOMAP, it's a conservative system for, and importantly, it's compatible with Hindley-Milner type systems. So you can sort of add it on to an existing system in a reasonable way, which is what we did. Anything that can be inferred can also be inserted explicitly. So it's very much like a classic type system with classic type inference. You can always choose to put the type and a type annotation yourself explicitly. Type checking is, of course, based on some heavy machining, which is ILP. But the problems tend to be simple, and the solver tends to be quite fast. And we've implemented this in FuthArc. It's not really production ready yet, but we're working on it, and we have a little bit of work to do on that. And check out FuthArc up there. There's also a blog post that I wrote about AUTOMAP that goes into all this in more detail. And there's also, you can check out me, and just as a quick ad, I'm looking for a postdoc or a job, if anybody has one. And that's it.
Questions?
Thanks for the nice talk. Thanks for mentioning SAC, because I was always thinking, well, we are a statically typed rank-polymorphic language. And I wonder a bit why you do this wrap thing. Because we have, in principle, similar problems. And we came up with a different solution. That means we keep the scalars.
Yeah.
And we have basically different versions of these elaborated functions, basically array versus array, array versus scalar, scalar versus array. And that is, for our case, very important to keep this as a kind of recursion termination in the type inference. And I wonder now, why do you blow up a scalar to an array of infinite size that you then bind to the shape of the other stuff? And not only that, I mean, you never want to execute it this way. You only want to, then you have to fuse it away, because otherwise it's terribly inefficient. So why do you do this?
So no, in practice we do what you do. So it is inefficient in practice, because so the reps there are sort of just a helpful thing. In the end, we actually fuse the reps into the bottom of a map, and we actually don't manifest the replication. Yeah, I guess. Right. So that in practice we actually don't do that. So if you
why do you do then this detour?
the detour doesn't actually happen. It never gets manifested anyway. We do the detour to express the constraints. Essentially, it was a way to explain the problem in some sense.
Is it a complicated way to express the problem?
It's the simpler way. It's the more general way. If you don't, otherwise you're specializing for different cases, right? This is a completely general approach, and then it gets optimized into something that's efficient.
Yeah, so if I understand this correctly, if it can find a valid rank polymorphic treatment, it'll apply it, right?
If it's not ambiguous.
Yeah. So there's a space of programming where you would like to be able to say, I'm rank polymorphic in these particular ways, but otherwise, if it's not this particular type of rank polymorphism, I want to give an error. So I can think of, where you might want to handle scalars going up to any arbitrary rank, or maybe vectors applied. But if we've got a matrix and a cube, well, those shouldn't scale up, or something like this, right?
Yeah.
Does this just sort of bypass all of that? And because you could, even if you insert some explicit ones, I think if I understand this correctly, it'll just, if anything's missing, it'll just add it, right?
Right.
Okay.
So if anything is missing, it will. If the minimum solution is there's only one of them, it will just add it, and that's what it will be. In practice, we've found that what you intended is pretty much what happens. Usually, the programs are sufficiently constrained that there's only one possible rank correct solution in that sense.
Is there any way to say, like, to create an error condition where yes, we could have been rank polymorphism here, but we're intentionally not being?
No, but maybe there should be. And of course, you can always explicitly, write what you want without rank polymorphism, right?
Yeah, thank you for the talk. I'm interested if you can have you can think of sort of infinite dimensional arrays as functions as being infinite dimensional arrays, and you want it in mathematical notation, since you're trying to sort of simplify things down and say that your code can represent the underlying math more directly. Like, you might want to perform operations where your inputs are functions, might be functions, or they might be primitive like scalars or something. Can you see a way to extend this to where you're sort of having rank polymorphism, but allowing your these functions as infinite dimensional array representations?
I'm not sure I entirely understand, but we do actually support higher order functions, so you can't actually automap on functional inputs themselves, but I don't think that's what you're asking.
Well, I'm thinking you might just want to say f plus g,
yeah,
right? And then whenever you provide an argument, it applies f and g to the argument, for example, and then just adds them or something.
Yeah.
Something like that
Yeah.
is what I have in mind.
I don't think we I don't think we support that. We should talk about that after. I don't think I totally understand.
Yeah.
Okay.
We're about out of time. Let's give Robert another applause.
I think let's take everything off.
Robert will continue like this.